Okay, we're going to have a quick review of our concepts here for energy. I'm just going to come up with a couple of situations, or maybe 5 or 6 of them, and just recall how we were looking at the world with respect to energy. First scenario, we have somebody's just standing on the ground, and we are going to be looking to ask questions about each energy problem the same way. Does it have any potential energy? Does it have any kinetic energy? Recall that with physics, we are looking to find the way that we're going to analyze the problem. Thankfully, in physics class, you're told it's energy unit or momentum unit. But in real life, when you look at it, you can take any one of those approaches. When you get to the point where you're solving things mathematically, you're going to need some values to do that. So that's when we decide what method by which we'll look at a problem, given what variables we can measure in the moment. So potential energy is a question of relative altitude. If you have nowhere else that is being referenced in a problem or that you're comparing an object to, then we will say that it has no potential energy, because potential energy equals mass times gravity times height, and if the height is not above anything else, then we say that it's irrelevant or equal to 0, and our potential energy equals 0 joules. For kinetic energy, it was a question of motion. If an object is moving, then it has kinetic energy. We have a substitution for kinetic energy of this, which gives us access to the variables that we are examining. The object does have mass. Is it moving? No. It has no velocity. Therefore, its kinetic energy is also 0. It is possible for something to be just standing there with no energy that we're going to be looking at. We're not talking about energy from food and so on. We're talking about energy we can do things with. Next example. Someone running. This person just running on flat ground. There's no increase in altitude at any time. And in this particular problem, we're going to just be focused on right at that moment. So if we asked ourselves, does this person have any potential energy, we would say there's no altering of height at any time at this, since we're looking at it in a moment, and therefore our EP will be 0 joules. If there's any kinetic energy, that means there's motion, and there is motion, as we can see right there, and so we will end up saying that our kinetic energy equals 1/2 mv squared, and maybe we can measure that velocity and that mass and find some value for it. Third example. Now somebody, again, we're just going to say this is at a moment. So somebody's running up a hill. Since we're not referring this to any other altitude, we get the same situation that we had before. Even though they're running up a hill, we're not comparing it. We don't know where the bottom of the hill is, don't know anything about the top of the hill. We'll just say there's no potential energy with reference to anything else right now. But they do have kinetic energy. And so from there we can begin to analyze what's going on. Now we got to the point where we were looking at problems that had more than one location, and we started using concepts referred to as the conservation of energy principle. And the idea was that if we are comparing 2 points that we can compare the energy of those 2 points, and we can find out if some energy was added, any was lost. The first type of problem that we were looking at had no gain of energy or loss of energy in the situation. So somebody could be running at point A. They could be running at point B as well. Maybe at the top of some rise. We referred to, when we were trying to analyze this, we referred to positions A and B, and then we looked to compare those 2 positions. These positions have a different altitude, so we indicate that altitude as a difference in height. And now we can say that at point B there is some potential energy. And we consider this at 2 points then. We have at A, the potential energy at A equals 0, since there's the lowest point. Hoping you can remember this conversation that we had. We have for kinetic energy at A, again we're just asking ourselves, is there kinetic energy? Is it moving? Yes, it is moving. So we may make this substitution. A substitution motivated by what the problem gives us for values. So notice we're not forming equations quite yet. We're just about to, but anytime we are doing physics, we first think, how am I going to analyze this system? In this case, we're analyzing it with respect to energy. And then can I get an equation out of it? Is something supposed to equal something else? And if energy is conserved, whatever energy there is at A will be the same amount of energy at B. It may be in a different form, but the same amount of joules. So at B, we ask ourselves the same question. Is there any potential energy at B? And yes, there is, because there's an altitude there, different from another location. So at B we have potential energy. Now there's also some kinetic energy, as we can see by the drawing. And if they had to continually put energy out so they can keep their speed going up that hill, then there's going to be some gain that they have there. And you will know if you run up a hill, you have to keep exerting your muscles. You keep on applying a force. So there's going to be some gaining of energy. And there may be some loss if there's some friction. Right? Maybe you dragged your foot in one of your steps, or the wind was blowing against you as you were running. So what we learned to do is to compare these 2 locations. So we have the energy at A, and we have the energy at B. On the way to B from A, we have maybe gained some energy and lost some energy. This equation here indicates that all the energy that is affecting the situation is accounted for. That's conservation of energy principle. So now from here we can fill in our spaces. What was that energy at A? Oh, at A we just have kinetic energy at A. We had a gain. I'll just say EG instead of E gain, minus E loss, EL instead of E loss, equals the energy at B, and mgHB, plus a 1/2 mv squared. From here, the questions become more specific. And the challenge that we have as physicists is when we look at a problem, we first of all think about how am I going to analyze that problem, and then we consider the mathematics that comes out of it. So now that I have formed an equation, now I can start plugging in values for things that I'm being given, and find things that I'm not being given. So lastly, a possible substitution that we talked about is each E gain is going to be equal to a force that's being applied. I'm going to call this FP times the distance over which it was being applied. So if the force was even the whole time, in this case it's tough to say so, so we might have a bunch of energy gains. Every time the person steps and applies a force over a particular distance, they get a little gain in energy. We could have a whole bunch of those added up together. And E lost as well. There could be some force of friction over some other possible distance. So we can see that we can analyze a problem in real detail, or if we're in physics class, we normally narrow it down and we make it a little bit more accessible, so we don't have too many variables we're considering.